Hello guys, good evening. Few minutes, we'll start the session. Few minutes more. Yes, Anurag, yes. Okay. So I think the last class we have discussed about electronic configuration. Hunt's rule we have discussed. Yes or no? Tell me the last thing that we discussed last class, where
Sir,
we stopped.
yes, subshells. Sir, excuse me, sir, can you hear me?
Hunt's rule. Fine. Okay. Is it fine?
Yes, sir.
Okay. So last few things we need to discuss, and then we'll move on to the next chapter in this. Okay. Poly exclusion of Bohr we have discussed. Have we discussed the examples of, just a second, Madhav. Have we discussed the example of electronic configuration chromium copper? Okay, fine, fine. I got it now. Wait, yeah. Suppose electronic configuration we need to draw for draw the electronic configuration for the first one is hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, fluorine, sodium. For all this, draw the electronic configuration. So we know the energy order. The energy order is this. Last class I have given you already this thing. Am I audible to all of you? Arnav is not getting me. What about others? Arnav, you can rejoin. Okay, I think there's a problem from your side because all other can hear me. So you can rejoin. Yeah. You don't know my name, Shashwat. My name is this. It's Gaurav Sinha. Then what? Acha, my this one name, uh, host name, right? Yeah, I have changed that. I have changed that. Okay, not an issue. I'll rename it in the next session. Let it be. So, electronic configuration. The first thing we should know is the atomic number, right? Which is 1 for hydrogen, 2, 3, 4, 5, 6, 7, 9, and 11. The atomic number we have here. Nothing. It's just the first thing we are discussing, Anurag. Okay. So electronic configuration, we discussed last class that the electron is a distribution of electron in the orbital, right? An electron fills into the orbital according to the energy of the orbital from lower energy to higher energy, right? One orbital can have maximum 2 electrons, right? So if you see this, we have S subshell. S subshell has only 1 electron and it can have maximum 2 electrons. If you talk about P subshell has 3 orbitals and each orbitals can have 2 electrons, so 6 electrons. D subshell has 5 orbitals, maximum 10 electrons. F subshell can have 14 electrons maximum possible. Right? So with this reference only, we'll distribute the electron in the what we say in the atom, correct? So hydrogen has only 1 electron. So you see, we'll start from here. 1s, 1 electron we have. So 1s1, the configuration is. For this one, 2 electron. So 1s2. Lithium has 3 electron. So 1s can have maximum 2. Then the third electron goes into next higher energy orbital, 2s1. Fourth electron will go into 2s, again 2s2. It is 1s2, then 2s2, that is 4. Fifth electron will go into 2p, and 2p can have maximum 6 electron. One will have here, if you talk about for carbon, so 1s2, 2s2, 2p2, nitrogen 1s2, 2s2, then 2p3, fluorine 1s2, 2s2, 2p5, and sodium 1s2, 2s2, 2p6. 10 electrons. Then after 2 picks, the next higher is 3s. So it is 3s, 1 electron left, 3s1. I'll give you some more, Madhav. Finish it first. These are the very basics one. No, I didn't forget. Intensely, I did not give.
Sir,
Yep.
so how do you represent the core, like the noble gas core? Like
As
if
in,
you want to represent only the valence shell.
In terms of noble gas, you are saying
Yeah, so like
Yeah. argon and then 4s2 3s2 4
yeah,
pieces.
like on Google I saw, so the electronic configuration, it has the noble gas and then the valence
I'll
shell.
discuss that. See, noble gas we can use. I'll show you. We've just
Okay.
started. Excuse me. Copied this one. Did you understand this? Just you have to follow this path like this. And whatever cells orbitals are coming in the path, you have to give electron into that shells. Okay. Depending upon their capacity. SPDF, this is the capacity we have maximum. Finish, all of you? Okay. Now we have one more rule in this, and that is write down. That is Hund's rule. Hund's rule. Write down the statement and then we'll see the rule, what it means. Statement, write down. In an orbital, I'll also write down, wait. The statement is in an orbital, pairing of electron is not done unless all orbitals belongs to the same subshell. Are singly occupied. What is the meaning of this statement? We have copied this down. I'll explain this. Okay. You see, these are p subshell, I am assuming, and this boxes represents the orbital in this subshell, because it says what? When all the orbitals belongs to the same subshell, Means the orbital belongs to d subshells are dxy, dyz, dzx, dz square, d x square, y square. Okay. Orbitals belongs to p subshell is px, py, pz, right? So it says in an orbital, the pairing of electron is not done unless all the orbitals belongs to the same subshell are singly occupied. Means orbital belongs to the same subshell must have at least must have one electron. Then pairing is possible. Pairing of electron is possible. Suppose this one here, this one, suppose we have, it is 2p1 configuration, p subshell 2p1 configuration, this is 2p2 configuration, this is 2p3 configuration, this one is 2p4, this one is 2p5, excuse me, this one is 2p6. And these are what? These are the three orbitals belongs to the cell subshell P, that is px, py, pz. Here also we have px, py, pz. And same thing here we have for the other three. Okay. So when you have 2p1 configuration, first of all, you see if there is no electron present in this orbital, the orbital is empty, right? At this stage, when the orbital is empty, I want you to write down these things in your own language into your notebook. Just in short, you write down so that you can understand what discussion was going on. What I said, that when the orbitals are empty, then the energy of these orbitals are same, and it is known as degenerate orbitals, right? Degenerate orbitals. So all these orbitals belongs to this subshell P, has equal energy. Now when electrons, we have 2p1 configuration, it means one electron is trying to fill into this orbital, right? It is trying to occupy the space in this orbital. So this electron can go into any one of these orbitals that we do not know, right? It can go into px, py, and pz because all three orbitals has equal energy, right? So it can go in any one of these orbitals, right? And the first electron that enters into any orbital, that electron we assume to have clockwise orientation, and that we represent up-headed arrow like this. So for just an assumption, we write first x, y, and z. So first electron goes into px, then py, and then pz. That is the assumption we take. But it can go into this also and this also because all three orbitals has same energy. Now suppose you have two electrons, like in this case, two electrons trying to fill into this orbital. Then one electron comes over here. The next electron goes into which orbital? According to Hund's rule, this will go into the next orbital, which is here. Pairing is not possible now. If it is 3 electron, then one electron will go into the each orbital first. I'm sorry. 1, 1, and 1. Like this, the distribution of electron takes place in the orbital. Okay. So pairing is not possible unless this stage is there. I'm talking about p subshell. If you have D, then first 1, 2, 3, 4, 5, and then pairing takes place. Okay. So pairing is possible when we have this particular configuration. Then we have 2p4 configuration. So 4 electrons you are trying to enter into this orbital. So out of 4, we have 1, then 2, 3. When we have this, all the orbitals belongs to same subshell are singly occupied and clockwise orientation. So fourth electron will go into any one of these three orbital having anti-clockwise orientation, right? 2p5, when 5 electron enters into this orbital, so first all the orbitals are singly occupied like this, and then the pairing takes place, fourth and fifth, anti-clockwise orientation. No, it's not. I'll talk about the direction. First, let me explain this. If you have 6 electron, then what happens? We'll distribute the electron like this. 1, 2, 3, 4, 5, and 6. So this is what it means. Okay, pairing is not possible unless all the orbitals belongs to the same subshell are singly occupied. Did you understand the rule first of all? Tell me. Right now, since electrons are rotating about its own axis, this rotation we do not know actually. Okay, again I repeat this. 1 second, Bharat. See, in any subshell, you have a given number of orbitals, correct? So, according to Hund's rule, what he suggests that all the orbitals belongs to the same subshell must have one electron singly occupied, one electron present over here. After that, only the pairing takes place. Like suppose if you have 2 electron, just a second. The point here is, suppose this is a p subshell we have, right, and it has 3 orbitals, that is px, py, and pz. Px, py, and pz. So if you have suppose 2p 4 configuration, suppose if you have, right, so you cannot do like this because you know one orbital can have maximum 2 electrons, so you cannot directly do this. This is not possible. It is not right. It is wrong. According to Hund's rule, what you need to do, you have to do this. You have to do this one. Again, I'm doing this just to make you understand. Okay, you have orbitals like this, 2p4 configuration. So what happens first, all the orbitals takes one electron like this, and then we'll start the pairing like this. This is Hund's rule. Read the statement. In an orbital, the pairing of electron is not done unless all orbitals belong to the same subshell are singly occupied. This is what the rule is. Correct? Fine. Right. So, as far as the orientation of electron is concerned, the electron can be clockwise, can have clockwise orientation or anti-clockwise orientation, that we do not know again, and we don't want to get into this discussion also actually. Why? Because first electron we assume to have clockwise orientation, means if you have up-headed arrow like this, if it is written up-headed arrow wherever we have, it means the clockwise orientation. Clockwise orientation. No, it's not. Like, yeah, it's relative. It's relative, you can say, but the electron that enters into the orbital, the first electron, is assumed to have clockwise orientation. Yes, correct, Anurag, you can say that. But the first electron is clockwise. That's why we always write up-headed arrow, the first electron for. Now, since it is clockwise, right, and when the second electron tries to enter the same orbital, if the second electron has or technically I should say fourth electron, because second electrons will come over here, third electrons will come over here, fourth electrons, then pairing takes place for p subshell. So if the fourth electron tries to enter into this orbital, first electron has already clockwise orientation. If the fourth electron also has clockwise orientation, then there would be repulsion, and hence that is not possible, right? To minimize the repulsion, when electron is trying to approach here into this orbital, this clockwise repels this clockwise orientation. So this electron changes its orientation from clockwise to anti-clockwise, or this fourth electron prefers to have anti-clockwise orientation in order to have minimum repulsion. That's why the fourth electron we place like this, and it is anti-clockwise orientation. Did you get it? Tell me, no doubt. That is what Hunt's rule means. If you have, suppose, D7 configuration, I'm assuming a configuration here. Suppose we have D7 configuration. This is 1, 2, 3, 4, and 5. Configuration is D7. D7 configuration. So D7 is what? All the orbitals will be singly occupied first. So 1, 2, 3, 4, 5, 6, 7. This is the D7 configuration. Clear? No doubt? Okay, this is Hunt's rule. Okay, write down the electronic configuration. Anyone, like I said, we do not have any control in which orbital the electron goes, right? So it can go into any orbital, can be py, can be pz, can be px. But convenience, like what the assumption we have, or by convention, what we'll write, we always write x first, then y, and then z. That's why it is written in that order. Otherwise, the electron can go in any one of the orbitals. Write down the electronic configuration for argon, electronic configuration for calcium, then scandium, phosphorus, chromium, iron, then copper. Yes, box diagram, I'll tell you what it is. See, actually, no, box diagram you don't have to write down, just write 1s2, 2s2, 2p6 like that. One more thing I'll tell you here, this box actually represents one orbital, because every time it is difficult to draw this dumbbell shape, right? So we usually take the reference of this box. This means it is an orbital, one box, orbital, and orbital. That is what the box diagram we have, okay? But for this configuration, you don't have to draw the orbital, the box diagram. You can write down the order like that, 1s2, 2s2, 2p6, and so on. What is the atomic number of argon? Could you tell me the atomic number of argon? 18. Atomic number of calcium? 20.
20.
Scandium? 21. Phosphorus? 15. Chromium? 24. Iron? 26. Copper? 29. From hydrogen to zinc at least. Better if you memorize till krypton, but to zinc you must memorize the atomic number. Now you write down the electronic configuration here. Okay, one more guys, one small request to all of you. I would request all of you to write down the notes properly during the class only. You don't expect me to send the PDF notes after the class, because we are going to change this particular thing, because we got to know that some of the students, maybe not from your class, maybe from the other batch, they don't write down the notes properly. That's why from the last 2 class, probably if you see past 1 or 10 days, 1 week, I'm not sending the PDF notes on the group. However, I'll send it for today, right? But you never know. Maybe for some class, maybe next class I won't send. So I request all of you to write down the notes during the class only. Okay, last week, many of you have asked me the notes for the last class. Okay, and I have already, I had deleted that. So I could not give you that time. I request all of you to write down the notes during the class only. Done? Okay. So the electronic configuration here for argon is 1s2, 2s2, 2p6, 3s2, 3p6. For calcium, it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, right? This one you see here, from 1s to 3p6 here, this represents the argon configuration, right? And argon is an inert gas. That's why we can also write the electronic configuration in terms of argon. And till here, I'll write down Ar simply. That Ar represents 18 electron, and then we have 2 more, so 4s2. That is what it means. Okay. Now in this one, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d1. Okay, 3d1. If you write down in terms of argon, this electronic configuration would be argon, then 4s2, 3d1. Okay, 15. This is no, we don't. We cannot write that. It's wrong, Advik. Acha, neon. You are writing it down. Neon 3s2. That it is not wrong if you write this, but we write in this way only so that we can have. See, till here it is same. No, 18 electrons till here it is same. That's why we write till here. There's no point of writing down neon here and then there's all these things here. The purpose of this is if you have a very long electronic configuration, then we can write in a shorter way when we use argon over here. What extra, Weber? One s2, 2s2, 2p6, 3s2, 3s2, 3p3. Okay, you can write neon here. That's not wrong. Neon, then 3s2, 3p3. It is not wrong. You can write like this. Okay. This would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Have some patience. I know you are going to object over here. Have some patience. Okay, I have written it. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. This one 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Okay, all these configuration we have, correct? But these two are not right here. This one is not right. This one is not right, and this one is also not right. These two are wrong. The correct one is what? The correct one is, in presence of this two, will have 4s1 and 3d5, and this one would be 4s1, 3d10. Why it happens? Because this 3d5 has exactly half filled configuration. Exactly half filled configuration. Half filled configuration means all the orbitals are singly occupied, one electron each present in the d orbitals. Half filled configuration and symmetrical also. We can say symmetrical arrangement.
Sir,
Yes.
so then why does this not hold true for silicon, sir? Because for silicon also it is 3s2, 3p2, right? Sir, so wouldn't 3s1 and 3p3 be more stable, more symmetrical?
See, energy gap is the factor. I'll discuss that. Let me finish this. I'll discuss that. Why it is not true for S&P transition. Okay. Here what happens, you see. This one is exactly or fully filled configuration. Fully filled configuration. And again, symmetrical arrangement. Symmetrical arrangement means symmetrical arrangement of electrons in the orbital. Like if you draw 3d10 configuration, all the orbitals are fully occupied, completely filled. 3d5 configuration is this. All the orbitals are fully occupied, completely filled. 1, 2, 3, and then 4. 1, 2, 3, and then 4. Right? If you draw the orbital diagram, you'll get 1, 2, 3, 4, and 5. Here we get 1, 2, 3, 4, 5, and then pairing 6, 7, 8, 9, 10. You see, all the orbitals are have one electron here. That's why it is symmetrical arrangement, and this gives extra stability to the atom. Symmetrical arrangement gives extra stability. Extra stability, and hence it is more stable. Here also we have extra stability, hence it is more stable, and electron forms this arrangement. Okay. So now if you see what happens, if you look at this, why it does not take place in S and P, like 3s2, 3p2 that we have, the question that you asked. Okay. So why it is not happening here? Because you see the orbitals, one factor is the energy factor here. Suppose it is, this is the third shell we have. Okay. And in the third shell, first we have S, then P, and then D. Okay. I'll just draw it a bit small. And we have a fourth shell, which is this. Which is this, right? So this energy gap, it is a transition of electron actually. From 4s to 3d, there is one transition of electron, and hence the configuration becomes this. Okay, why this transition takes place? Because the energy gap here is not that great. The energy gap between 4s and 3d orbital is not that great. That's why the electron delta E is not large here. And hence the electron can jump into this. Transition is possible here. But S and P orbital, if you see 3s and 3p, the energy gap is relatively large. And that energy gap is sufficient enough which prevents the excitation of electron from S to P orbital. That's why this thing is true only for S and D orbital, like 4s and 3d we have here. Understood this? All the atoms try to have lesser energy state, and the distribution of electrons in orbitals affects the overall energy of an atom, right? So when we have symmetrical distribution, the overall energy is less. The atom is more stable in that case. That's why whenever it is possible, obviously depending upon the energy difference, whenever it is possible, there is a transition of electron in order to have more symmetrical arrangement and lesser energy state. Understood this? Tell me. Did you get it? That's what I said, Anurag. That's what I said, that whether it is fulfilled configuration or half-filled configuration, it's a relative thing. If you have only one electron here, you see this. If you have only one electron here, then there will be some energy, right? If you have one electron like this, one here and other one is here, it will have some energy, means unsymmetrical arrangement. So it has been observed that when here in this state, the energy that we have, and in this state, the energy that we have, this has lesser energy, more stability over here because of the symmetrical distribution of electron. All the orbitals has one electron each, right? So this arrangement of electron decreases the overall energy of the orbital or atom, we can say, and hence the stability we have. Like this, we won't say that fully filled and half filled configuration has lesser energy. Overall, the energy decreases and stability increases. See, all are electrons, right, Anurag? So if you have unsymmetrical distribution, correct? So there will be some repulsion in the electron. We have to find out the state, the arrangement of atoms where the repulsion is minimum. Then only the stability will be more. So repulsion will be minimum when the arrangement is symmetrical. If suppose this one is repelling this electron, right? So other one, it is going towards the other electron, right? So net thing is what? Net arrangement, the net force or net repulsive or attractive force, whatever is present over there, that decreases the energy of the atom over there, right? So it is basically the arrangement of electrons which affects the energy. See, this one you see. You have two possibilities. Okay, this is 4s, this is 3d. This is 4s orbital and this is 3d orbital we have. 3d shell we have. So one arrangement is this, when the 4s has 2 electron and 3d has 4 electron. Right? So here we have some repulsion in 2 electrons. And the other arrangement, if you talk about, and the other arrangement is this. When this electron jumps from here into this orbital. So this has certain arrangement of electrons. And here none of the orbital has 2 electrons. Right. So obviously the repulsion will be less here in comparison to the other configuration. That's why this one is more stable. This is the easier way you can understand this. Here we have 2 electron, more repulsion, less repulsion. You can get it. But the thing is here, the overall energy decreases because of the symmetrical arrangement of electron. Right, that is what the thing we have. Now electron, first of all, electron fills into the orbital in order to get, in order to get more stability of the atom. So obviously the electron first go into 4s and then 3d. But in the case of chromium and copper, the electron won't go into 4s. It goes, first it fills 3d because it is getting symmetrical arrangement here, more stability. And then it is left with 1 electron that goes into 4s orbital. So a little bit of different arrangement we have here. The overall objective is what? To get lesser energy state, which is more stable. In order to get more stability only, the distribution of electron takes place in this manner. Okay, understood? Now, this is Hans rule. We have discussed it. Last part of this chapter we need to discuss, that is nodal surface, correct? But before that, one small thing we have to understand here. Two small thing, in fact. So write down just one formula we have here that you need to keep in mind. Write down, that is spin multiplicity. Spin multiplicity, we calculate this with the formula 2 summation of s plus 1. This is the formula of spin multiplicity. How do we calculate this? Suppose we need to find out the spin multiplicity of carbon in excited state, right? For carbon in excited state, so carbon has 6 electron. We draw the electronic configuration of this. That is 1s2, 1s2, 2s2, and 2p2. The electronic configuration is this. If you draw the box diagram of carbon, that would be this 1, 2. This has 2 electron, and 2p has 1 electron. Right? This is the thing we have. This is in ground state. This is in ground state. In excited state, what happens? 1 electron jumps over here to make a bond. this carbon goes into excited state and one electron jumps into the vacant p orbital, and in this case it has 4 unpaired electron. 1, 2, 3, 4. This is the excited state we have. Excited state. Okay, so spin multiplicity is what you see here. This is 2s, this is 2p, this is also 2s, 2p, and 1s we also have here, which has 2 electrons like this. So spin multiplicity is this, and how do we calculate this? You see, we have 2 summation of s means the number of electrons with clockwise orientation, that is 1, 2, 3, 4, 5. So 5 electron with clockwise orientation means plus half is the spin multiplicity for this 5 electron, plus 1 electron has anti-clockwise orientation, 1 into minus half, bracket close, plus 1. This is the spin multiplicity of carbon, and when you solve this, you will get five into plus half, 2.5, 2.5 minus 0.52, that would be 5. A spin multiplicity of carbon atom is 5. That is how we calculate. Transition of electron requires some energy. So when the carbon atom is going for reaction, so in the reaction we need to provide that energy, then only the electron excites. No, we do not have orbitals here. It has second shell and there is no orbital after 2p. No, chromium was not in excited state. The configuration of chromium is 4s1 3d5. It is not excited state. Two p electron, if it get excited, the electron should go into the higher orbital. No. Do we have orbital here? No, we do not have. Do we have 3d? Second shell 3d orbital is not there. No, third energy shell we do not have over. Third energy shell, we do not have it there. It is only for second shell we have. See, transition of electrons takes place in the same subshell, first of all. Right, transition of electron takes place in the same subshell. If you change the shell or subshell, right, means within second energy shell, transition takes place. I'm not talking about chromium and copper here. Chromium and copper has an exceptional case due to symmetrical arrangement. Correct? But when the electron goes into the higher energy shell, it does not mean that from 2p it will go into 3s or 4s or 5s. That is not possible because all these transitions requires energy. Right? Electron transits from one orbital to another depending upon the energy available there. Right? So in 2s and 2p, the electron can transfer from 2s to 2p. And what is the point of this? First of all, 2p to 3s you are talking about, there is no possibility. Why? Because 2p has only one electron. It won't go into 3s because 3s has higher energy than 2p. Here what happens when the electrons present here, so we'll have certain repulsion, and when you provide energy to this, then this electron transfers over here, and hence it has 4 unpaired electron. That's why carbon can form 4 bonds with any other element, and it is tetravalent in nature. Right, so its transition is not according to your choice or our choice, right? From one shell to another shell, transition is difficult. First of all, it requires high energy. Number of unpaired electrons, with that only we'll find out with this particular formula, spin multiplicity. This is the formula we have used, you see. 5 clockwise orientation, 5 into plus half. 1 anti-clockwise orientation, 1 into minus half, plus 1 into 2 gives you this. Yes, but spin multiplicity, we do not count only for unpaired electrons. These electrons also we have to consider. Okay, you said 2p has higher energy than 2s. You know the difference between 2s and 2p and 3s and 2p? You know this difference? If the transition of electron is possible in 3s, so we'll have certain energy required for this. If that energy is more than the energy required for this transition, then which transition takes place? Anurag, tell me. 3s and 2p had some energy difference. 2s and 2p had some energy difference. That is what? Usually what happens, 2p to 3s transition is very difficult. And it won't happen. Before that only 2s 2p transition takes place. And suppose hypothetically, if I assume your point that the electron transfers into 3s, then also it has 3 electron, unpaired electron. So carbon in that case will form only 3 bonds. That is not possible. Carbon is tetravalent, forms 4 bonds, and 4 bonds it can form only when it has 4 unpaired electron. And to get 4 unpaired electron, this electron has to excite over here. Okay, so this is the thing we have. Transition of electrons in excited state takes place in the same subshell. Okay, subshell we can say, or we can say in the same shell. That is a better word. Okay, 3s, 4s 3D transition is kind of exceptional case we have in case of copper and chromium. Right, symmetrical arrangement, more stability. Nothing much we have over there. So this is how we calculate the spin multiplicity with this formula. Okay, this is one thing. Now, one last thing here we need to discuss before nodal plane, that is the orbital wave function. We have discussed it already. The orbital wave function psi. Write down one last thing, one question they ask on this. orbital wave function. This psi, I have already told you that it contains all the informations of electrons. It contains the energy, like it contains the information related to energy of an electron, because in case of chromium and copper, the transition of electron is possible and it gives symmetrical arrangement. It depends upon 2-3 factors. One is the difference of the orbital, that is 4s and 3d, right, and transition of electrons also. So in that case only, the energy gap is not that high, and hence electron can jump into the higher energy orbital, that is 3d orbital. That is why it is possible for chromium and copper only. See, the question is, why those two elements the exception we have? It is because of 3s and 4d electron, 3d and 4s electron, the difference in these two orbitals, in these two subshells. The difference in energy is not that great, and hence the transition of electron from 4s to 3d is possible over here. If you go to higher energy orbital, like suppose we have next is 4d and 5s, suppose I am taking, for example, then in that case also the energy difference is there, and that is, that difference does not let this 5s electron to jump into 4d. So it is one kind of exception we have that we observe only in the case of 4s and 3d, nothing much. No, in this we do not have. In transition element, we have a bit here and there. We'll discuss that in grade 12, not now. Okay, so we know this orbital wave function. It contains all the informations about energy and the distance of electron from the nucleus. And this also gives us the probability of finding an electron around the nucleus, right? This wave function has two parts actually here. This is the radial part, psi r, and it has the angular part. Angular part we represent by the angle it is made by it, theta and phi, right? Radial part and angular part. Only two things you need to know here, nothing much. The angular part, that is the distance of the electron from the nucleus, r. This psi r is the radial part we have. The radial part, and theta and phi is the angular part we have. Radial part and angular part. This radial part, it depends on the value of n and l, principal quantum number and azimuthal quantum number, right? So this radial part gives us an idea about the size. Idea about the size. This is the angular part, and this gives us, first of all, it depends upon depends on the value of L and M, the quantum number, size of the orbital L and M, and it gives us the idea of the shape. Shape of orbital. Okay. So size means what? Suppose n is the principal quantum number. So if the value is, we have n 1s, 2s, then the shape, the size is what? Size would be like this. 1s will be like this, and 2s would be like this. This is the size of the two orbital. Right. If you have 2s, 2p, sorry, if you have suppose 2p and 3p, the orbital we have 2p and 3p. So both has dumbbell shape. So 2p, suppose this, then 3p would be larger than this. This is what it means, right? That's why the Schrodinger wave equation, it gives us an idea of the three quantum number n, l, and m.
Sir, so using the radial part, we can't compare the size of 1s and 2p.
1s and 2p, no. Spherical we cannot compare. No, dumbbell we can compare with dumbbell.
Okay, only the same structure we can compare.
Same shape we can compare. Means how do we compare a sphere and a dumbbell? That's not possible, right? We can say 3p has a larger lobe than 2p. Got it? These are the two things we have. Now you'll get this question in the exam, and they'll ask questions like this. They'll give you the notation here. Like the question is, we'll have psi, and here they'll write down some number like this. Suppose 4, 2, 0. Like this, some number they'll give you, and they'll ask you that which orbital is this? Means orbital related question they'll ask you. Which orbital is this? Right? So you should compare this with this one. When you have psi, and here the number which is written, it is in this order, n, l, and m. Means if you compare this to what is the n value? 4, L value is 2, and M value is 0. So which orbital is this? This is 4, L value is 2. Which subshell? Which subshell? D. M is equals to 0. It is Z square. So it is 4D Z square the orbital is. Understand? Clear? So only this question you'll get, nothing more than this. Okay, N, L, and M value. Okay, the last topic for this chapter we have, write down. Write down nodal surface. Just a second, I'm coming. Wait. Okay, write down the definition. Nodal surface, write down. It is a surface at which it is the surface at which the probability of finding an electron is 0. Nodal surface is the surface at which the probability of finding an electron is 0. Okay, this is a nodal surface. Okay, so we have a relation of psi, that is wave function, because we are talking about the probability of finding an electron is 0. Correct. Probability of finding an electron is 0. So we must have to use the psi square function, right? That is a probability density function or wave function psi, we can say, right? So what happens here? Different orbital. This nodal surface, we have two types. Means basically you have two formulas which with that you can easily find out the nodal surface. We have two types of nodal surface actually. Write down. Of nodal surface we have. The first one is spherical node. A spherical node. We also call it as radial node. A spherical or radial node. Number of spherical or radial node is given by n minus L minus 1. These are the quantum numbers. Okay. The second type we have, that is non-spherical or angular node and its formula is L. These are the two types of nodes we have. They may ask you, what is the number of nodal plane for this particular, orbital? Okay. Mute, guys. Charan, mute yourself. Okay, these are the two nodes. If I ask you, what is the total number of nodes? That would be the sum of these two, n minus 1. This is the formula we have. Okay, so first of all, you should know this formula. Okay, how to find out the nodes in any orbital. Correct? This is one part of it. We have a graphical representation of this also. Right? How do we represent the graph of it? Okay, that is the relation of psi and r, then psi square r square, and then the probability with this. Okay, so basically, if I ask you, find out the node for 1s orbital. First of all, one thing you see, this spherical node, we can represent on graph. We can show this on graph. That at certain distance, we have this surface, spherical surface, where the probability is 0. Angular node, we don't represent on graph, basically, right? So if it is 1s orbital, so number of spherical node is what for 1s orbital? A spherical node for 1s orbital is n minus L minus 1. So n value is 1, L value is 0, minus 1, that is 0. There is no spherical node. Angular node, if you can count here, is also 0. So there is no node here for 1s. Right. Now, based on this, if you draw the graph, little bit I am taking the help of experimental relation because we do not know the relation of psi and r. But if you draw the graph of psi and r, the graph you will get like this. I'm just drawing it down. 3 graphs I am drawing here. Okay. What happened? Okay. This side we have psi. That is a wave function. And it is the radial distance from the nucleus. This is r. This is the probability density function, psi square, and this is R. And this is the probability. Four pi R square dr into psi square. This is the probability we have, this axis, and this is the radius. Did you understand this term? 4 pi square is the surface area of a surface of a sphere, and dr is the thickness of that. So 4 pi R square dr into what? I'll explain you, wait. Suppose we have a surface here, a spherical surface we have like this, and the radius is R. So what is the surface area for this? 4 pi R square. Okay. 4 pi R square surface area. So this is the radius R we have from this point. This is the radius R. Okay. And the thickness of this radius of this surface is dr. This is dr, this thickness. This is the thickness we can assume as dr. Right, so this surface area, if you multiply this with the thickness, it gives you volume, right? So volume of this sphere is what? The surface area of the sphere, 4 pi R square into dr. Correct, because the thickness I am assuming here as dr. This thickness is dr I am assuming. Correct? And we already know that this psi square is the probability density function, right? So the probability of finding an electron is equals to the probability density function psi square. It is probability per unit volume into the volume, and volume is for this surface is 4 pi R square dr. So when you integrate this, you'll get the probability. Is it clear now? Tell me. Yes. So this graph is with probability with radius. It is a probability density function with R, and this is wave function with R. For 1s, right? This is for 1s we have. So the graph here we have, you see, the graph for psi and R, which logically we cannot find out because we do not know the relation of psi and R, but this graph is observed to be like this. Psi square and R graph also go steeper, and it goes like this. Goes like this. Won't touch the x-axis, go like this. Okay. This is the probability density, a probability graph, probability in this. So at some point, you know, it is the nucleus here. In the nucleus, there is no electron present. So it starts from the nucleus, right? It starts from the nucleus, goes to the, increases like this. And at some point, the probability is maximum. Then it comes down and goes like this. Just a second. Right, so it will go like this, increases and comes down. It won't touch the x-axis because at this point, the probability is 0. But for 1s orbital, there is no nodal surface here. That's why it is not the, it won't touch the x-axis. Yes, it won't touch the y-axis, it is asymptote here. So this is the graph of 1s orbital, This is the probability graph, which is the important one. Sometimes what happens, they'll give you this graph and they'll ask you to find out for which orbital the graph is, right? So since this graph does not touch x-axis, that is this one, hence the probability is never 0 here, and that is possible with 1s orbital. Did you get it? Okay, you copy this down. I'll discuss the another one. You will have more clarity into this one. Copy this down. No, this we can draw the graph with the relation of psi and r, the radial relation that we have. Obviously, the equation we do not have, hence we cannot predict this. Okay, the next orbital you see, suppose the second one, we are taking 2s orbital. So for 2s orbital, what we can write? The number of spherical node, could you tell me? Tell me the number of spherical node. A spherical node is equals to n minus l minus 1, 2 minus 0 minus 1, that is 1. And the number of angular node, that is L value, which is 0. There's no angular node here. Okay, so when you draw the graph of this one also, I'll draw it quickly here. So this graph is again psi and r. This one is psi square and r. This one is the probability, that is psi square 4 pi r square dr, and this axis is the radius we have, r. Okay, so here the psi square and r graph goes like this. From here it comes down like this and it goes up, but it won't touch the x-axis like this. It won't touch this. Okay, wave function can be positive, can be negative, and that's why we have the graph like this. But if you draw this psi square, so here Psi square cannot be negative. It is always positive. This negative part will draw the mirror image of this to draw the graph of psi square. That would be like this. It comes down, and at this point, it goes up, comes down and go like this. Okay, so this point is the node we have. This point is the node. One node we have, this is the point where this psi square is 0 means probability is 0. So when you represent this in probability graph, we have one node here. The graph goes like this. It will go up, comes down. We have a node, so it will touch the x-axis, and then again it goes up to maxima and comes down, and it goes like this. This point is the node. So obviously it has a distance, certain distance, the node is present.
Sir,
Yes.
so won't the node touch the, like, won't the node be a nodal region? Won't it, like, how will it be a point, sir? Because the probability
No,
will
on
be,
the graph, see, on the graph, this means what? From the nucleus, at this distance, we have a node. That is what it means. But when you draw this, the surface, I'll show you how do we draw it. It just represents that at this distance, one nodal surface is present. And what is a nodal surface? It is a spherical surface.
no, sir, I meant that shouldn't this graph touch the x-axis for not only at one point, at, like, it should touch the x-axis for some time and then go up, because it should be a nodal region where the probability is 0, right?
Wait, your voice is feeble. Can you talk louder?
Yes, sir, I meant that in the graph of the probability of finding the electron, so shouldn't the graph touch the x-axis not only at one point at the node, it should touch at the full at the nodal region which is extended in the x-axis, sir, because the probability of finding electron is 0 for, like, between first subshell and second subshell. So the radius is not only at, like, particular radius, it's like a region from, like, say 2 millimeters to 3 millimeters.
Yeah,
Just giving you-
no, see, you are getting it wrong. I'll explain this. Why? See, you have a certain distance, this distance, correct? Now this means what? We have a nucleus. First of all, the atom, suppose the atom is this. Let me draw the diagram here. Suppose the atom is this. Right. In this atom, we have a nucleus, which is here. And around the nucleus, at this distance from the nucleus, this distance, we have a region. We have a spherical region actually. We have a spherical region where on this region, the probability of finding an electron is 0. Means whatever the distance we have, suppose this distance is, I'm assuming this distance is, suppose R1 we have, this distance is R1. Same distance we have here also, this is R1. So at this distance from the nucleus, this is R1. You will have a spherical surface. Obviously, we have some thickness of this also. You will have a spherical surface, and on that surface, the probability of finding an electron is 0. So it is a region only. It is not a point.
Okay, sir, but then say, sir, if you draw the first shell that is n equal to 1 and n equal to 2, so then between those two shells, there's a region, right? It's not only a single radius. There's a region.
Yes,
in between the two shells.
spherical surface. Yeah.
Yeah, so like the two concentric circles are there, the region between that.
Correct.
So that consists of more than one value of R, right?
No, for a one particular value, that's what I'm telling you. For this value, we'll have a surface, we'll have a region, spherical surface, where the probability is 0. It's clear, no? We have only one node, correct? So we have only one spherical surface. What distance from the nucleus? This distance from the nucleus.
No, sir, but then it says that the probability is 0 to find
Yes.
the electron.
Yes.
So that is in the full region between the two electron clouds, right?
No, it's not the full reason. Why you are taking this? You are talking about this entire region. The probability is 0. For suppose 1s and 2s, if it is right.
Yeah.
I am telling you what, that in between this we have a spherical surface. In between this, at a distance this r1, on that sphere the probability is 0. It's not the reason. It's not the entire reason between the two.
So
Right.
so only in the middle of the two it is exactly 0.
Let's not phrase this way, middle of the two. You simply can say that at this distance from the nucleus you will have a spherical surface where the probability is 0. That is it. When you say spherical surface, it is a region only, it is not a circle.
No, sir, but
Tell me.
sir, like see, imagine the first circle you drew is 1s,
Hmm.
sir, and the second circle you drew was 2s.
2s, correct.
So the region between that is empty, right? There's no electron over there.
That we cannot say. That we cannot say. If this is the sphere of this distance, then it is possible. If the distance, suppose I'm giving you a value here. Suppose this is 5 meter, for example, correct? And this is, suppose we have 12 meter, the radius of this parabola sphere, correct?
Yeah.
And we have a nodal surface at 7 meter. Then the nodal surface will be 7 meter from this point. You can draw a circle, a sphere over here.
So, but isn't the probability of finding electron 0 from 5 to 12?
No, that we cannot say. That's what you are not even accepting that definition of it. Whatever we can have a sphere of this radius and this thickness, possible?
Yeah.
This thickness and this radius. We can have a sphere of this radius and this thickness where the probability is 0. We can have it. But it is not like we have always this condition. I am giving you one general and simple answer for this. What I am giving you is the graph that you drew here, it must have certain distance from the nucleus. So at this radial distance, you will have a spherical surface within the atom where the probability of finding an electron is 0. You are talking about that we can have a surface here. Here we have electron and here we have electron, but in between these two we do not have electron, which may not be true. Depends upon the case.
Okay, so in the graph of psi square, so the point where it touches the x-axis is 7 meters, not 5.
Yes, exactly. That's what that's the point I'm trying to make. Whatever the distance,
it has to touch only at one point.
Right. Whatever the distance we have here, at the same distance we have a spherical surface. That's what I have written, R1 and R1. You see this? R1 and R1. At the same distance we have a spherical surface where the probability of electron is 0. So this is the nodal surface. If you can write down this is a nodal surface we have where there is no electron, this circle. According to the graph I am drawing here, with respect to that, it must have certain thickness, right? Because in sphere, and this is the nodal surface we have precisely, you can see.
So anything except that 7 meters, the probability is not 0, but it's very close to 0.
Yes, anything. That is not our concern.
That's it. Okay.
It can be anything, but not 0.
Yes, sir.
You understood? Again, you see, I'm explaining. I'm just concluding this. You will have this graph, and at this point, the psi square graph is touching the x. What does it mean? That at this distance from the nucleus, psi square is 0, and when psi square is 0, the probability is 0. That's why we have one nodal surface here. Why it touches only once this x-axis? Because we have only one spherical node. And remember, I told you already that we can draw only a spherical surface here. Angular we cannot draw. Okay, so 2 things you should keep in mind. The probability graph always starts from origin. any confusion in this? The probability graph always starts from origin. Any doubt in this? Because in origin is nucleus, and nucleus electron can't present. Correct? So this graph always starts with nucleus, and the number of peak that you are getting, right? It is one more than the number of node present into this. We have one node and we have two peak. These 2 points write down. The probability graph always starts with 0, origin. The probability graph always starts with 0. Second point, the number of peak just a second, Shreyas, is one more than the number of node. The number of node. Psi is the wave function, Shreyas. Okay, wave function is like amplitude function for a wave. So wave travels like this, correct? Up and down like this. So above the axis we consider this as positive, and below the axis we consider this as negative. Right? That's what it means. Amplitude can be positive and negative because it goes up and down. That's the reference we are taking. Above the axis is positive, below the axis is negative.
Sir?
Yes.
So then also for the psi square 4 pi r square dr graph, so shouldn't the peaks be opposite? Like because if the
It will
r
come
is
down
less.
below the axis.
Hello?
Yeah, tell me.
Yes, sir. I was telling for the third graph. So if the r is less, then the max probability will be higher than when the r is more, right?
I didn't get you. Max probability will be high when the R is more. Why? Why is that so?
No, sir. When r is less, when the shell is closer to the nucleus, so then the probability will be of finding electron will be more than when the shell is farther from the nucleus, right? So shouldn't the peak be opposite, like the?
No, it's other way. As you go closer to the nucleus, the probability decreases because electron cannot present in the nucleus. And this graph, this is just a representation. This graph, it could be like this also. Could be like this also.
Yeah, so shouldn't the second mountain be smaller? The second.
Possible, depends upon the atom. Both possibility we have. In the book, if you see, they have drawn the graph like this only. Okay, but it is possible that depends upon the atom that we are going away from the nucleus, the probability decreases. Similarly, if you come closer to the nucleus, we know in the nucleus also the probability is 0 for finding an electron. Right, so we cannot always say as we go away from the nucleus, the probability of finding an electron is 0 always. So this could be anything. It can be down, it can be up depending upon the atom. But yes, we definitely have two peaks, one more than the number of node present into this. Okay. Tell me. Psi square is, Madhav, psi square is the probability density function. I have discussed this in Schrodinger wave equation. Okay, psi square is like it represents the electron, the intensity of electron at a point. If psi square is maximum, probability of finding an electron is maximum because the intensity is maximum of electron. You can compare this with psi, you can compare with the amplitude of a wave, light wave, right? And psi squared you can compare with the intensity of a light wave. No, we won't do that. That is not in our syllabus. No, psi squared cannot be negative. That's why we are not drawing the graph below the axis here. negative probability does not make any sense, correct? And that is the reason we have taken psi square here. Yes, that is what, so fine, we have drawn it, no? We've drawn it, no, but this negative part in terms of probability, it does not make any sense. That is why we have taken psi square here, that whatever the negative thing is there, it becomes positive like this. Which graph? This one and this one. It represents the intensity of electron at any point, right? It represents the probability of electron at any point around the nucleus. This is intensity, this represents probability, right? So here the intensity is 0, means probability is 0. Mathematically also it is correct. Psi square is 0, this term is 0. This is, yes, these two I have explained. This one is the amplitude, right, of the electron wave. Amplitude of the electron wave, which can be positive and negative. So this will go below the axis as well. That's why we have written this. Yes, actually this is a bit, confusing if you try to understand each and every point here at this level. It is a bit confusing because it is all, like I said, it is quantum mechanics. But to simply what you can understand with these two formula, just whatever, if you're not getting it, like you can think about it and then we can discuss this later. You need probably more time on it. Just a second. What you should do here, we are doing the last part. Let me finish this. What you should do here, mostly they'll ask you one question that I'll give you after this. When we finish this, I'll show you what kind of question they ask. You should know what is nodal surface. You should know the formula with which we'll find out the nodal surface, correct? With a given orbital, what nodal surface is there, that also I will discuss. With graph, what you can conclude, that you should know. This represents probability. Where the graph touches the axis, the probability is 0. And with the help of this graph, you can easily find out that this graph is for which orbital. Like suppose I have given you this graph and I ask you, this represents which orbital? 2s, 2p, 3s, 2p, 3s, 2s, or 1s. What is your answer for this graph? Let it be whatever I have written here. Just remove it. This graph we have, and you have 4 options, A, B, C, D. This graph represents which orbital? What you will do? You will find out the number of nodes for this orbital. The number of nodes for 3s is what? The number of nodes for 3s is 2. The number of nodes for 2p, total nodes, you tell me. We have only one angular nodes, right? Only one angular nodes we have in 2p. We have 2s, one spherical node, 1s orbital has no nodes here. Is it clear? Are you comfortable with these values? Tell me. All of you, please respond. Yes. So obviously you can eliminate these two possibilities, right? Yes or no? Guys, you are not involving. Please respond. We can easily eliminate these two, correct? Now in this one, because in the graph we have only one node, correct? But we know this is the angular node, and angular node we cannot represent on the graph. We cannot show this because angular node has complex shape, right? We have sphere, dumbbell, double dumbbell, leaf-like structure. So angular node has a complex shape. If you are going to draw the angular node, you'll be drawing the angular nodes only in the exam. It's not about the drawing test, right? That's why we don't draw angular nodes on paper, because it's complexity. One simple thing, right? So since the graph is given, so we only have the spherical node possible, which is there in 2s, hence the answer is this. So this kind of questions you will get based on the graph. You can have many questions, but those things they won't ask. That is the best part here. And you will not lose marks on this. I can bet you on this. It's very simple kind of question they ask. Okay, one more example I'll show you for 3s, and then we'll move on from this. You see, in the graph, they won't show angular node at all. If only angular node is there, you can eliminate that option easily. Sure. Okay. Fine. Now you see, if I draw the graph for 3s orbital, I want all of you to try this on your own. 3s orbital. Try this. First of all, you find out the number of spherical node. That is n minus L minus 1, 3 minus 0 minus 1, it is 2. And the number of angular node is L, and that is 0. 2 spherical nodes. Now we'll draw the graph. The 3 graphs we'll draw here. See.
So we can only draw the graph for s orbitals, not for p, d, and f, right?
No,
because
for 2p
that
also we
angular-
can draw. For 2p also we can draw.
So, but then for that, for 2p angular node is 1, right? So you told we can't represent angular node.
So spherical node we can represent. Angular we won't represent into that. For 2p, suppose there is no spherical node, so the graph won't touch the axis, right? And angular node we won't represent. I'll draw that also. Wait. It's the same graph. It goes like this for 2p. A curve like this, a mountain like this, it would be. For psi square, and probability. 3 graphs we'll have like this. I'll show you just a second. So this value is 0. Okay, this is psi, and this is r. Psi square r, and this is psi square 4 pi square dr integration and r. See, the number of node that you are getting, equal time this graph will cut the x-axis. It goes like this. Two nodes, so 2 times it will touch the x-axis. So it is plus, this is minus, and this is plus. Further, it won't touch the x-axis, right? Now, the psi square of this will just get the mirror image of this one. Everything will be as it is. It comes like this. Touch the axis, it goes up, comes down, goes up, comes down, like this it goes. Further, it won't touch the x-axis. Here also, the probability curve, it will touch the x-axis twice, like this we can say. Okay, so these are the nodes we have, spherical nodes. These are the nodes we have, spherical nodes. So whatever this distance is, R1 and R2, you can draw 2 spherical surface at this distance, R1 and R2. That would be the angular node sorry, spherical node for 3s orbital. Okay. Now, a few facts here you should know. I'm sorry. Suppose we have 2p orbital. We won't draw the graph here. If you want, you can draw. It is a mountain like this. It comes psi like this, psi square also like this, and probability also like this. Like this only we get. Okay. Because it has only angular nodes that we cannot represent here. We won't draw that angular node. So the number of spherical node here spherical node is n minus L minus 1, n is 2, L is 1 minus 1 is 0. Angular node is equals to 1. Okay. So if it is px orbital, so it has one angular node for this. So for px orbital, the angular node is yz plane. It is the angular node. Means the perpendicular plane we can say. Node is this. YZ plane is the node. Because the electron is in this x orbital, so perpendicular for this plane is YZ plane, there is no electron present, hence it is the YZ plane. Similarly, if you take py orbital, perpendicular to this plane is what? ZX plane, and that is the node we have. PZ orbital, we have XY plane, and that is the node. Okay, so this you must keep in mind. Similarly, for 3D orbital, you see, for 3D orbital, the number of spherical node, could you tell me what is the number of spherical node? And angular node. Angular node would be 2, spherical node would be 3 minus 2 minus 1 is 0. Right. So it has two nodal plane, nodal spherical node, right? So if it is dxy orbital, so perpendicular plane for this is yz and zx. These two are nodal plane for this orbital, that is dxy. Similarly, for dyz, you can have xy and zx. dxz, you can have yz and xy plane. Perpendicular plane you can take. Here we have only one exception. Write down this point. Note. dz square, there is no nodal plane for dz square. This you have to memorize. It's an exception. There is no nodal plane for dz square, but the angular nodes of this, is a cone. In this shape we'll have. We don't have a plane, but the angular node of this is a cone, and that's why we don't represent it. Like I said, it's a complex shape, and hence we do not represent the angular nodes there. Correct. So these are the things you should keep in mind for nodal plane. Very direct and simple question they'll ask you. It's not much difficult. Okay, very simple question. You won't lose marks over here. Okay, now one kind of question that I have already told you, that graphical questions, how they ask. Okay, another type of question. Okay, you see this question. What is that TOSC, Anurag? YZ plane. For dx square, y square, YZ plane is the node. YZ and ZX also we can consider. Yes, YZ, ZX. What 11th slide? Just a second. There's nothing in 11th slide. This one? Just a second. This one. What is the nodal plane for s orbital? Which s orbital you are talking about? Can be anything. 1s, 2s, 3s, can be anything. Dx square, y square has two nodes. Okay, the one nodal plane is directly coming towards the observer, you can imagine. Okay, perpendicular to the plane of dx square, y square. And the other one is horizontal to us, bisecting the xy axis, means horizontal and perpendicular, you can imagine. Himanshu, which s orbital you are talking about? Yes, here I have done this. It means that we have a surface, a spherical surface at this distance, where there is no electron present. No, it's 3D, Anurag. You are not getting it. It's 3D actually. Like I said, one nodal plane is bisecting the xy axis, horizontal. Left to right, you bisect it. Right. Other one is perpendicular to the plane coming towards us. So when you have imagine a plane, it is like this. Yeah, that's what. The perpendicular to the plane we have. Yeah. See, how can I draw this? See, first of all, if you have axis like this, xy axis, so one is bisecting this axis. How do we draw this? This is a 3-dimension, no? So if you bisect this half, this side above the this thing screen, and one half below the screen, that is one thing. One is along this line. If you bisect this perpendicular towards us, observer, that is the 2 nodal plane we have. It's 3-dimensional. I cannot draw this in 2D. Okay. Okay. Solve this question. You see, the wave function is given, and with this question, I think you will have a little bit of clarity. How do we get those graphs and all? See, the wave function is given. Wave function for 3s orbital is given, and that is psi of 3s equals to 1 by 81 root under 3 pi 1 by a naught 3 by 2 open bracket 27 minus 18 r by a naught r by a naught plus 2 r by a naught cube bracket close e to the power minus r divided by 3 a naught. This is the wave function of 3s. So like this will have the wave function of each and every orbital. Okay, it is given, and it says the wave function of 3s is this. It has a node. It has a node at r equals to r naught. It is the radius, and a naught is the first radius, first Bohr radius, we can say, first radius, we can say, the ground state. Find the relation between r naught and a naught. Could you think of this question? What is the possibility we have?
What is A naught and R naught?
R is the radius, and a naught is the first radius we have.
R naught?
R naught is the information given. Like we have no.
Oh, okay. So it's like a variable.
Yeah, that at that particular distance, R naught, there is a nodal surface.
Okay.
Yeah. Done. Yes, Aditya, that's correct. Because R naught is the nodal surface, so you have to put psi is equals to 0. Very simple question. It looks very complex here, right? It appears to be very complex, but question is the quite simple question we have. You see, it is simply given that at R is equals to R naught, we have a nodal surface, correct? So when you substitute here R as R naught, then psi 3s would be equals to 0. So can we write this at R is equals to R naught, 3s equals to 0, and we substitute this in this equation. So we get 27 minus 18 R naught by A naught plus 2 R naught by A naught cube equals to 0. I think there's a mistake here. It should be square, not cube. It should be square here. Okay. Now you can solve this quadratic for R naught by A naught. That would be minus B plus minus B square minus 4AC. So 54 into 4 is 216. Okay. 216 root over of it divided by 2A, that is 2 into 2, 4 we have. Right. Now you can solve this, you'll get the relation of, you'll solve this, you'll get the relation of R naught and A naught. You'll get approximately when you solve this, you'll get 18 plus 10.4, 28.4 divided by 4. So this would be, no, this divided by 2 will get here. So we'll get, okay, you'll get this 56.8. You can solve this, you'll get the answer. And that would be 14.2 approximately. So R naught value is 14.2 A naught. This is the relation we have. One relation is this. Because since we have plus minus here, so we'll get one more value of it. We'll get this, means exact value. I'll write down how do we get this. The exact value we get here is like this. Answer will be this only. You'll have 18 plus minus 10.4 by 2. So when you solve this, you'll get 18 plus this, that is 14.2 when you take positive sign, or when you take negative sign, it would be 11 and 7. So 7.6 by 2, that is 3.9 approximately. Yes. .8 approximately. So R naught value is this, or R naught value is 3.8 A naught. When you solve this, you'll get this expression. Calculation, I can't do anything. No, it's not a cube, it's a square. That's a mistake in the question. By mistake, I've written it to cube. It's a square. And then you can solve this for a quadratic equation. Nothing I haven't done. Whenever you get this question, right, you have no other choice but to put psi is equals to 0. That is it. They can also ask you that what is the nodal radius for this particular condition. So in that case, you need to find out R value, correct? Whenever it is nodal plane, psi must be 0. So I substitute psi 0 here, and then it is a square plus 2ab plus b, a square plus 2ab plus b square. It is in that form, right? Or simply it is a quadratic, so you can use it for x equals to minus b plus minus b square minus 4ac root over by 2a. This is the simplest one. It is, don't think about this equation. It is not there in our syllabus, right? Just you focus on, it is talking about a node at this point. So at node psi value would be 0. So when you substitute r is equals to r naught here, this becomes a node and psi would be 0. When you substitute 0, all these things will go on, only this thing is left. Then you solve this, simple. When you solve this, you'll get Pranav. When you solve this, you'll get it. I haven't solved it. Right, you check, you cross check it. The value I have written directly here. Okay, wait, I'll solve this again, just a second. I'll solve this for you. Leave it. See what we get here. Minus 216, you'll get 108. So you'll get here 18 plus minus root over of 108. Okay, divided by 4. Root over of 108 is what? What is the value of root over of 108? $10.3. 18 plus minus 10.3 divided by 4. So we'll get here 28.3 divided by 4, or we'll get 7.7 divided by 4. So what is this value? We are getting 7 point something. 28.3 divided by 4, it is 7.07. This value is, and this value is 7.7 divided by 4, 1.9. 1.92. So the value is R naught is equals to 7.07 A naught, and R naught equals to 1.92 A naught. This is the possible relation of R naught and A naught here. What is, see, this is the spherical node. This question is not talking about the spherical node. Why do you want to? It's not like that you know something, then you need to find out in every question. The question is not about what kind of node it is. It is spherical node or angular node. It is not. The question is what? We need to find out the relation of R naught and A naught. And it is given that we have a node at this particular point, right, at this distance from the nucleus. We'll apply the condition of it. When R becomes R naught, psi becomes 0. We'll use that. Obviously, because we have 3s, so 3s will have spherical node only. There is no angular node for 3s. So we have 2 spherical node, right? How many spherical node we have for 3s? How many spherical node we have? 2, right? So we should get 2 values of radius where the probability is 0. So this is the 2 value we are getting. You see this? It's very simple. We'll have the nodal surface at these 2 points, these distance from the nucleus. Mathematically also you are getting it. It is proved. 3s has two spherical node, hence two value of r we are getting. Understood? All of you understood this? Tell me. No doubt? Correct. Okay. One last question for this. You need to find out how many nodal planes are there how many nodal planes are there in the atomic orbitals for the principal quantum number n equals to 3. Yes, they'll give you the formula. If they ask you this question, the relation of psi and r they'll give you, because we do not know. See, one more thing I'll tell you here, you don't have to worry about this relation, okay? Because the graph that we draw, it is based upon the relation of psi and r. So this kind of complex equation will get when you solve the equation, correct? So this solution is not there in the syllabus. So obviously they have to give this relation in the exam. Otherwise you won't be able to solve this. Don't worry for that. Tell me the number of nodal planes. Total nodal planes you have to tell me. How many total nodal planes? Means with n is equals to 3, whatever orbital is associated, count the nodal plane for them. No, it's not. It's not. No, it's not. It's not. See what I said. No, Anurag. What I said. The orbitals associated with third shell. We have 3s, 3p, 3d. Count the nodal plane for each of these orbitals. No, it's not that. You are you are saying all the answers probably. No, that is not. That is something else, Hariharan. N minus 1 is not the formula. Advik got the right answer. Very good, Advik. Anurag, close but not correct. No, Namrata, no. See here, simple one. Which all subshell we have in third shell? We have 3s, we have 3p, we have 3d. Correct. So 3s has only one s orbital, right? One s orbital, and it has zero nodal plane. Right? We know S has no nodal plane. Three P has three orbital. 3px, 3py, and 3p. Yes, Anurag, correct. 3pz, and each of this orbital has one nodal plane. Each has one nodal plane. It means we have total 3 nodal plane here. It has 5 orbital, 3d zx, xy, yz, x square y square, and 3d z square. Now in this one has no nodal plane. It has nodal cone, right? Not a plane. No nodal plane. And this, each of these has two nodal plane. Total 8 we have over here. Right, each of these orbitals has two nodal plane. Dz square has no nodal plane. So total nodal plane is what? 8 plus 3, that is 11. Yeah, 3s has a spherical node. It is not a nodal plane. Question is about nodal plane here. A spherical node we have. Right, a sphere is not a plane. That's why we are considering it as 0. Right, so answer would be, for this question, the answer is 11. So this kind of question they ask in nodal surface. They can ask you what is the nodal plane for this orbital, how many nodal plane present, dz square one is important, it has no nodal plane, very important this one, and that equation related question they ask. That is it. Plus how many nodal plane present into this, nodal surface we have into this. So radial angular node formula, you know, with that you can find out. These 3-4 types of question they ask, nothing much. Clear? Understood? Okay, so fine, we are done with this chapter. We'll take a break now. We'll resume the session at 6:50 and we'll start a new chapter. Okay, take a break. Periodic properties will start. Take a break, guys. Hello. Can you hear me? Okay. Okay. So the next chapter we are going to start with the next chapter we are going to start with is periodic properties. Okay. So this a particular chapter, it is basically the first chapter of the inorganic chemistry. Okay, the first chapter of inorganic chemistry. So basically here we are not going to see any numerical questions like we had in some basic concepts of chemistry or atomic structure. You will have a theoretical questions into this, right? Conceptual questions you will get. Yes, there are few things, in fact many things you have to memorize here, right? But certain terms that we are going to understand here, like you remember in GOC I have discussed electronegativity concept. Remember that? Organic is easy, Shashwat. Okay, then see, I don't get this thing. No, this concept of easy or tough. It's basically something is easy for you, and for someone it is difficult because he may be, probably he did not understand the concept properly. So if you understand the things, there's nothing tough here. But yes, there will be, the nature of the topic, maybe like, there are many things to memorize, to mug up. Maybe that could be a, the boring part of it, that you can say. But easy tough, I don't get into these concepts. It's just, if you understand it, fine. If you don't, you won't get it, right? You find it tough. Maths, basically the concept is the math is a very vast subject, right? But if you like maths, you won't be scared of it. Yes or no? So I don't get into this concept of easy and tough. Okay, try to understand this. Okay, you will get it, not a problem. Organic also, if you are finding it tough, just give it some time, revise the concept that has been taught, right? And get back to me if you have any doubt, right? If you run away from the topic that you are not getting in, you are not going into the right direction, right? Understand that. Anyways, so in organic chemistry, like I said here, we are not going to get the numerical questions. There are concepts. We need to understand terms. We need to understand factors affecting it. We need to understand that particular terms, factors will be using in the entire chemistry, whether it is physical, especially inorganic chemistry will use that. Okay, so here we are going to understand, for example, like I told you, we have used a term that is electronegativity that we'll discuss in this chapter. Okay, same thing, but little bit more we'll discuss, nothing much. Okay, so when you know all these terms, then we can, no, normality we'll do after this. After this, we'll start mole concept 2. There we'll discuss about normality, redox reaction and all will concept we'll do over there after this, okay? A small chapter, it won't take much time, but I think maybe, 2.5 class it requires, it depends upon you, like how much doubt you ask, that's all. So the point is, in organic chemistry, periodic properties, like I said, we are going to understand here about the periodic table, how the periodic table, designed, what is the, thought behind this, why we need periodic table, and then various trend in the periodic table. Like one thing you must know, as you go down the group, what happens in periodic table? Size increases or decreases? as we go down the group, size increases. This trend, you know, right? So these kind of trends we are going to understand here, right? What are the factors affecting the atomic size or ionic size? Okay, those things we are going to discuss. Okay, so the thing is, when they were, you know, scientists were looking at for different atoms, there were very few elements known, right? So that point of time, what happens? You know, they can understand the property of that particular atom, because suppose if you have 8 or 10 odd atoms known, then you can memorize the properties. There's no need to arrange them in a proper way so that you can keep that in mind, that what happens with what, right? But when the time of, like, when the study goes on and on, the research was, they were doing various different kinds of research, right? And that they get to know there are so many different atoms exist in the nature, right? So as the number of atoms increases, elements, different types of elements increases, this thing, like, to keep that, you know, properties and various other things for those particular atoms in mind, it becomes difficult. And they started looking for the arrangement of atoms in a particular way, based on their properties, based on their electronic configuration, based on their nature, many other things, right? So they started looking for the arrangement of atoms in a particular way. So in this way, they have given different theory. It is similar to the various atomic models that we had. Okay, various scientists, they started looking for the arrangement of subatomic particles, and they have given their own theory, which we call it as various atomic models. So here we have, once there are so many elements known, so we started looking for the arrangement of atoms so that it is easier for us to keep keep those properties for a particular element in mind. So in this way, we get different theories that we call it as the attempt to get the periodic table, right? And the final arrangement that we have of atoms according to their properties or atomic number, basically, that arrangement is the periodic table, the modern periodic table we have. Okay, so this theory, this entire, you know, attempt that is made, that we discuss under the development of periodic table, right? So first of all, you see, what are the attempts made for the development of periodic table? So write down. Quickly we'll finish this, because on this you are not going to get any question, right? So quickly you write down development, and in the the recent syllabus, they have removed this historical part of it. Okay, it is not there in the board syllabus. That's why we'll go quickly on this. Okay, development of periodic table. We cannot ignore this completely, because maybe, you know, in 2022, you know, they may ask you these things in the exam, JEE, or information must required, right? That's why I will go through it quickly. The first attempt was made by the scientist called Protz, right? And this theory, we call it as Protz theory. Protz synthesis, or Protz hypothesis, not synthesis. It's not a Protz hypothesis. Quickly write down. What he said, he assumed that all elements are made up of hydrogen, which was obviously the, you know, wrong, not correct, but yes, we have to go through once. He assumes that, or he suggested that all atoms are made up of hydrogen, which was obviously wrong, and we discarded it, right? And atomic weight for any element, what he says, the atomic weight of any element is equals to n, where n is the number of hydrogen atom present in it. Right? This is the first theory that we get for the arrangement of atoms. The second one is, and which is a bit important, that is Doberer triad rule. DOBER EINER, Doberer triad rule. Write down. He suggested that that within a group of three elements, within a group of three elements having similar physical and chemical properties, the atomic weight of the middle element is the mean of the other two, is the mean or average of the other two. This is what he suggested. Okay, for example, you see atomic weight is the concern. We have atomic weight, not number. Okay, keep that in mind. It is atomic weight. So if you take an example of lithium, sodium, and potassium, okay, the atomic weight of lithium is 7, potassium is 39. So if you take the average of the two, that is 23, is the atomic weight of sodium, and it follows Doberer triad rule. Okay. If you take calcium, strontium, and barium, the atomic weight of calcium is 40, and for barium it is 137, and the average value is 88.5. Right, that is the atomic weight of strontium. The exact, no, it's not for all the things, not true, only for few groups of elements. Okay, the exact value of strontium, the exact atomic weight is 88, but still it is close, so we can consider this. Right, the exact value is this. Okay, if you see sulfur, selenium, and tellurium, sulfur is 32, tellurium is 128, so that would be 160, and this selenium is 80, so it is valid for this also. Right, so this is the Doberer triad rule. Okay, all elements could not arrange this way, and that's why we discarded this particular. But yes, it is important in exam also. They have asked this question, that which of these groups of elements follows this particular rule, Doberer triad rule. Done. But yeah, they won't ask this year. We cannot say next year what happened because we are going to write the exam in 2022. No, so maybe they'll if the things get in place, then they will again introduce all these things back, right? So that's why we are not leaving those things. We can just go through it quickly. Okay, that's how we are doing. In board exam, you won't get this. They won't ask you these things in the board exam. That for sure. Right. Third one you write down. The third attempt made was Newland's octave rule. Newland's octave rule. He suggested, write down, if the elements are arranged in order to their increasing atomic weight, then every eighth element had similar properties to the first one like the first and eighth note in music, like sa re ga ma pa dha ni sa, right? So sa and sa, the eighth one, right? Sa re ga ma pa dha ni sa. So same thing we have here. If you arrange this atom, you see we have lithium, beryllium, then we have boron, carbon, nitrogen, oxygen, fluorine, and then sodium. We have sodium here, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and potassium. So if you compare this with the musical note sa, re, okay, so all these elements has similar properties. Like we have this one. If you compare this, and this, right? Similar properties. But yes, this thing was also not found to be correct for all the elements, right? And there is no place for inert gas. Inert gas was not discovered, and all elements could not classified on this basis, and hence we have discarded this. The next one is Lothar-Meyer curve. Write down, he plotted a curve or graph between atomic weight and atomic volume. Of different elements. See, all these attempts made with atomic weight only. Here also we have atomic weight and atomic volume. And he observed a particular pattern, and that pattern is, you see this graph here. The graph is this. Okay, this we call it as Lothar-Meyer curve. Okay, this is the curve we get. What he observed in this, that the electropositive element, that is the first group, group 1, alkali metals, right? The electropositive elements like alkali metals occupy the peak position on the curve. You see here, electropositive elements occupy the peak position. You see, lithium, sodium, potassium, rubidium, and cesium, right? These red dots are electropositive elements. Electropositive elements. Okay. Second observation is what? The less electropositive elements, that is the group 2 elements, alkaline earth metal, occupy the descending position. You see, lesser electropositive than this one occupies the descending position, which is this. See this beryllium, magnesium, then calcium, strontium, barium. Okay, this red one is the elements of group 2, right? The first one is group 1, lesser electropositive is group 2. No, it is not, Shashwat. Still, it is not clear. We cannot assure this on this. Okay. Metalloids and the transition metals occupy the bottom part of the curve. You see the metalloids and transition elements on the bottom part. Vanadium, cobalt, copper, zinc. This side you see. This side you see metalloids and transition elements occupy the bottom parts of the curve, right? More electronegative, like halogens, fluorine, chlorine, bromine, iodine, occupy the ascending position of the curves. Ascending position, right? So ascending position you see here. Here we have chlorine, bromine, iodine. Somewhere here we have fluorine, right? So ascending position of the curve, there is halogen atoms present. This kind of pattern he observed, like with a given mass, the volume occupies in this pattern. That is what he said, right? But the problem with this is that he concluded what with this particular graph, that the atoms with similar properties, elements having similar properties, occupy similar position on the curve. Like all electropositive metals occupy the peak, electronegative occupy the ascending part of the curve, right? Lesser electropositive, descending part of the curve. This is what he concluded with this. And he suggested, write down, he concluded on the basis of Lothar-Meyer curve, he concluded on the basis of Lothar-Meyer curve that the physical properties of the elements are physical properties of the elements are physical properties of the elements are the periodic function of their atomic weight, the physical properties of the elements are the periodic function of their atomic weight. Okay, so this was again a better result we get from this, and this conclusion actually that the periodic function of the atomic weight, the properties are, this conclusion becomes the base of the next attempt, which is Mendeleev's periodic table. Okay, so next you write down the fifth one. Wait. On the basis of Lothar-Meyer curve, he concluded that the physical properties of the elements are the periodic function of their atomic weight. Periodic function of their atomic weight. Okay, this is the conclusion of this. Next one is Mendeleev periodic table. Mendeleev periodic table, write down. He suggested that the physical and chemical properties of an element are the periodic functions of their atomic weight. Right? Physical and chemical properties are the periodic function of their atomic weight. He's again talking about atomic weight. Okay, so this is important. Physical and chemical properties are the periodic function of their atomic weight. Okay, so atomic weight we are dealing with, not number. Okay, he was the first scientist who actually arranged the elements in horizontal rows and in vertical column. Right, so the horizontal rows that he arranged here, the horizontal rows are called periods, and the vertical column are called groups. are called groups. So there are, when he give this particular theory, there are total 7 periods in the Mendeleev periodic table. There are 7 periods present. This also they ask in exam. And if you talk about the row, that is group, there are 8 groups. Only 63 elements were known, 7 periods and 8 groups were present that time. Okay, next write down. Each group, just a second. Lothar was correct. Yeah, it is not wrong. It's correct. It gives us an idea that the properties had some. It has some periodic order with the elements, but not completely correct because atomic weight he was taking. Because of atomic weight, only Mendeleev's also discarded after some time, right? But the conclusion that we get that physical and chemical properties could be in a periodic manner. It may get changed with the elements. So periodic thing was correct, but atomic weight since he has taken, that's why we discarded this later. Lothar-Meyerhoff. Okay, just a second, Pranav. Just a second. See, write down next line into this. Write down each group up to 7, not 8th one, up to 7th is divided into A and B subgroups, where A is for normal elements, and B we use for transition elements. B subgroups is for transition element. Transition elements, okay? Write down the 8th group. The 8th group consists of 9 elements. In 3 rows. Consists of 9 elements in 3 rows, and this we call it as transition metal group. Yes, so Pranav, there are some discrepancies in this theory, And that's why later on we discarded this also. It is also not completely wrong, but again, this is not valid for all the elements. It could not accommodate all the elements, and hence we discarded this particular theory also after some time. But this was the first attempt made in which we get a tabular form of the elements. We can arrange, after this only we started thinking of the arrangement of elements in a table like this. Right? Mendeleev, to some extent, he was so correct that there were some element for whom the position and properties, were well defined by Mendeleev even before their discoveries. Okay, he gave this theory, and for some elements which was not discovered that point of time, he left the position blank for those elements. Okay, so this was the biggest achievement of Mendeleev's we have. He could find out those things and could left the space blank for those particular elements in its periodic table, right? But then again, with the help of atomic weight, right, this arrangement of atoms was not observed to be correct for all the elements, right? There will be some difference in property here and there. So later on, this particular theory was also discarded, right? So defects is what? There is no certainty in the position of hydrogen. Few drawbacks of this point you write down, Mendeleev. Position of hydrogen is uncertain. Drawback of Mendeleev, write down. Position of hydrogen he did not fix. It was uncertain. Right? Then no separate position were given to isotopes. Last one, the order of increasing atomic weights is not strictly followed. The order of increasing atomic weights is not strictly followed in the arrangement of elements in the periodic table. Yes, fine. But there are other drawbacks also. Because of that only we discarded this. So the modern periodic table is just a little bit correction in Mendeleev only. Okay, we'll discuss that next class. Last point to write down. The order of increasing atomic weights is not strictly followed in the arrangement of elements in the periodic table. So this was the drawback. The modern periodic table is what? It is just the modified Mendeleev periodic table. Some corrections we do into this one and we get the modern periodic table. So what is modern periodic table? How the arrangements of atoms are there? That we'll discuss next class. Okay, guys? Okay, thank you guys. Thank you so much. Atomic structure, guys, on Learnist, there are 3 assignments uploaded, right? It's a mixed question. You must solve all the 3 assignments. Okay? All of you have Learnist credibility? You have credentials? All of you have, right? Fine. Those who did not finish it by the next class. Fine. Okay. Thank you, guys. Thank you so much. Take care. Bye.
Thank you, sir.
Thank you, sir.
Thank you.